Okay, hello everyone. I welcomes to all in our lecture series on expectation value of a physical observable A, which is represented by A cap within the angle bracket like this in quantum mechanics, which is very much essential for BSc, BTech, MSc, MTech and various entrance examinations such as CUET, CPET, JAM, GATE, NET, TIFR, etc. In this lecture series, we are going to discuss in detail about representation of expectation value of a physical observable A, some important questions on expectation value. Using expectation value, we have to verify the Heisenberg uncertainty principle. Okay, so let us start. In quantum mechanics, expectation value of a physical observable quantity, suppose A, in general, it is written as like this: A cap written in between angle bracket is equal to minus infinity to plus infinity psi star A cap psi dx upon minus infinity to plus infinity integration psi star psi dx is equal to minus infinity to plus infinity psi star A cap psi dx, and this denominator can be written as psi mod square dx. And if this psi is a normalized wave function, then this value will be equal to 1. Here A cap, here I written itself. Here A cap is called the operator of corresponding physical observable quantity A. Psi mod square is the most important here. Psi mod square is called probability density. It can be represented by rho. And this one, minus infinity to plus infinity psi mod square dx equal to 1, which is nothing but your total probability. And this is your probability density, means probability per unit length. Okay, because here this expression written in the form of 1D. In the form of 1D it is written. Okay, so if we are going to consider 2D, then it will be written in the form of double integration psi star A cap psi dx dy, and in case of 3D it will be written as psi star A cap psi dx dy dz, or it can be written as triple integration psi star A cap psi dqr. Okay, here I written in the form of 1D form. Accordingly, you can consider for 2D and 3D, right? Okay. Actually, in quantum mechanics, expectation value of physical observable quantity is nothing but average value or mean value, right? So how average value and mean value is written in this format, that we are going to discuss. In quantum mechanics, in general, the physical observable quantities are position, momentum, kinetic energy, potential energy, and total energy. So here, if I'm going to consider the expectation value of x or position along x-axis, here this is one dimensional. Along x-axis, it will be written as x cap. Along y-axis, it will be written as y cap. Likewise, along z-axis, it will be written as z cap. This will be written as what? Minus infinity to plus infinity psi star x cap psi dx by minus infinity to plus infinity psi star psi dx, which will be equal to minus infinity to plus infinity psi star. Here x cap value is your x psi dx, and the denominator will be 1 if psi is your normalized wave function. If we are going to consider px cap, the value is your minus I h cross del by del x. So it will be written in this format as minus infinity to plus infinity psi star minus I h cross del by del x psi dx. And if we are going to consider kinetic energy operator value, is your, this is nothing but your p square by 2m here, or px square by 2m. Px value is this one, so it will be written as 1 by 2m. This will be minus h cross square del square by del x square. If I'm going to consider square of this term will be this much, or it is written as minus h cross square by 2m del square by del x square. So if we are going to find out the tx cap, so it will be written in this format, that minus infinity to plus infinity psi star minus h cross square by 2m del square by del x square psi dx. Okay, this is nothing but dx cap or expectation value of this one. So this is the style that we have to write the expectation value of a physical observable quantity. But here the question is that why and how and why we are going to write the expectation value of a physical observable quantity in this format. Okay, that we are going to discuss in this video. For that, we consider a group of students. Okay, and here we tabulated the student age and the number. Suppose here total number of students are 100. In this group, total number of students are 100. Here number of students are 30 and the corresponding age is your 20. That means age 20, if we are going to consider, then how many numbers of students are there having the age 20? 30. Okay, age having 15, how many numbers of students are there? 25. 12 age, how many numbers of students are there? 25. Age 10, how many numbers of students are there? 20. So total students here you can see this 25, 25, 50 and 30, so 100. So here we have to find out the average age of this group of student, which is given table or in figure you can write also. So this is the simple numerical if we are going to consider by considering this group. Here I written something in bracket, try to focus over here. Here average age means physically meaning what? What is the physical significance of average age? Means what is the age that most of the students have that age. So here you can see 100 students are there but different ages, 20, 15, 12, 10. These are the ages we have in this group. So what is the maximum uh, probability or most of the student which age they have? So which age most of the students have, that is the so-called your average age. So how we are going to evaluate it? It is evaluated in this way, that the average age or age upon a bar, which is nothing but your average age, represented as average age, okay, is equal to x1 omega 1. Here x1 means 20. This column is represents xi, this column represents a wi. 20 age, how many students? 30. So we have to multiply these two, or we can write in general x1 omega 1, x2 omega 2, x3, this is omega 3. Okay, I'll correct, x4 omega 4 by omega 1, omega 2, omega 3, omega 4. This is the general procedure to find the average of this type of group or this type of data, you can say. Okay, so this mathematical expression can be written in this way by summation format. Here different ages are 4, so it will be vary, I will be vary from 1 to 4, xi omega I by omega I summation over y equal 1 to 4. Here also I have to correct. Okay, first I have to correct it. Okay, here I corrected. I equal to 1 to 4, I equal to 1 to 4, omega 3 and omega 4. Okay, okay. So if I really put the values of x1, x2 up to x4 and omega 1, omega 2 up to omega 4, then it will be written in this way. And finally, after calculation, we can find the value will be 14.75 or approximately you can say 15. Okay, so यहाँ पे the average age of the student of this group हमको कितना मिला? 15. So approximately 15 is the age that maximum student have. Okay, so here the average value is nothing but your weighted average. This is so called your weighted average. In mathematics language it is called the weighted average. Okay, because if we have, suppose generally we have 5 students having age 5, 4, 3 and 5. What is the average age? Just addition of these 4, that will be 5 5 10 4 3 17 by 4. This is the in simple language average. But if we have 5 page having a number of student, 3 4 age will be 2, like this whatever we have been discussed with this example or with this table. For that, it is called as your weighted average, nothing else. So here this average is named as weighted average value or mean value, or most important, your expectation value. Okay, so here expectation value or weighted average value of this group, how much we found? 14.75 or around 15, we can say. In general, weighted average value or expectation value of a physical observable, it can be represented by sum of weighted terms by total number of terms. Here sum of weighted terms is the numerator. Suppose n number of uh, different ages we have, or n number of variables are there, so the numerator will be written in this format: I equal to 1 to n xi omega I, or in addition format we have tried like this, and the denominator will be this much. So this is the in general way we have tried the weighted average of a physical observable quantity. Okay, okay. Now we have to consider here another example to find out the center of mass of this system, that is your a rod having the length 6 centimeter and discrete distribution of masses. Here you can see at x equal 0, 2 masses are there. At x equal 1, 1 mass. At x equal to 2, 3 masses are there. X equal 3, there is no mass. And x equal 4, 1. X equal 5, 2. X equal 6, 1. So here we found at different position of this rod, different masses are there. So where is the most of the mass will be concentrated, or the so-called what is the position of center of mass of the system, that we are going to find out. Okay, how we are going to find out? Here you just consider the rod is the uniform and the length is the 6 centimeter, and the total balls here how many? 2 3 6 7 7 and 8 3, so 10 number of balls are 10, and each ball has equal mass m. So each red ball equal mass. Okay, now the center mass of this system, or the position of most probable mass of the system, will be where? How we are going to calculate? We are going to calculate exactly what we discussed previously, the weighted average. Xi mi, this is the familiar formula for you maybe, but you just consider the previous example. The numerator we have tried xi mi by mi. So at particular position, what is the mass? That we have to multiply for each position by total mass. So at x equal to 0, what is the mass? Mass, suppose m naught, and x equal to 1. In general, if I'm going to expand it, it will be x1 m1, x2 m2, x3 m3 up to x6 m6 whole divided by m naught plus m1 up to m6. Now, if I'm going to consider m naught, means what is the mass or total mass at x equal to 0? Here at x equal to 0 total mass, if I'm going to consider each mass value is m, then at x equal to 0 the mass will be 2m. So this is nothing but m naught. So instead of m naught, we can write 2m. m1 is your 1. Here you can see 1 mass at x equal to 2, or m2 is nothing but 3m. At x equal to 3, no mass, so 0. At x equal to 4, only 1 mass is there, so m. X equal to 5, 2 masses are there, so it will be written as 2m. At x equal to 6, 1 mass whole divided by all the masses. So if we are going to just calculate, we can find 2.7 centimeter is the center of mass, or most important, the position of most probable mass. Okay, that means most of the mass supposed to be concentrated. That is your center of mass, and we found for this system where at 2.7. So this is at x equal to, so here it will be 2.5 around, and this is the position of 2.7. So the most of the mass supposed to be concentrated at 2.7, that is your center of mass. Keep it in your mind this example. we are progressing, that how the expectation value will be represented like in this format, that we are going to discuss in discussing. Okay. Okay, so we consider the discrete distribution of masses like this, and the center of mass how we can found by this formula. Now consider probability density, that is your rho equal to psi mod square at each point instead of mass for quantum dynamics. So here instead of mass, here at x equal to 0, the masses is your 2m, or this is your m naught, and this is your m1, like that. Instead of mass, you just consider psi mod square or probability density at each point instead of mass, because we are approaching the quantum mechanics, right? So here you can see a quantum dynamics, that a teeny particle, that may be electron or proton size particle, moving along one dimensionally, or here along x-axis I shown in the figure, along one dimensionally, then what is the position we are going to expect that most of the time we can found the particle, or what is the expectation value of this, expectation value of the position of this particle. Okay, so just I considered the previous example, the most of the, or the center of mass of this system we found by considering this formula. And if I'm going to consider instead of mass, probability density, because here uh, along x-axis it is moving, and each and every point it is continuous, it is not discrete. So here you can see at x equal to 0 masses are there, at x equal to 1 masses are there, but in between x equal to 0 and 1 the masses are not there. So if I'm going to consider what is the mass at x equal to 0.5 for this system is 0, like that at 4.5 is 0. But for this case, here you can see, for this case we could not say that particle is not at x equal to at x equal to zero point 0.5. At x equal to zero point 0.5 particle exist, at x equal to 4.5 also particle exist, and x equal to 3.5 also exist. Try to understand, it is most important. This is the discrete. At particular point at x equal to 0 mass is there, x equal to 1 mass is there, x equal to 2, but in between x equal to 1 and 2 there is no mass. But here we could not say that in between x equal to 1 and 2 there is not probability of observing this particle. That means probability we can observe in between x equal to 1 and x equal to 2. But if we are going to consider instead of mass discrete format, first we are going to consider discrete format. Instead of mass, if we are going to consider probability density at each and every point, that means x equal to 1 2 6 as like previous example, then in which way we have tried? We have tried in this way. For this case, the position of most probability of finding the particle will be written in this way. Instead of mass, I just written probability density rho I. What we discussed now, that probability density rho is not discrete. It could not be discrete because probability density at x equal to 0 exists, at x equal to 0.5 exists, at x equal to 0.6 also exists, at x equal to 0.7 also exists, at x equal to 3.1, 3.2, at each and every place point of this rod probability density we can found. So here probability density is not discrete. Here I clearly written in your note that in previous case we have considered summation representation due to the discrete distribution. So this representation or summation representation or addition representation, whatever we consider to calculate the center of mass in our previous example, due to discrete distribution only. But here it is not discrete distribution. Probability density, probability of finding the particle everywhere. It can be here, it can be here. So density, probability density can be observed at any point from x equal to 0 to x equal to 6. So it could not be a discrete dynamics or a discrete system. Okay, this is not a discrete system. So same thing I have been written. But in this case, distribution of particle is not discrete. It is not discrete. But previous one, if I am going to consider previous, it is discrete distribution. So we could not consider summation representation. In this case, distribution is continuous. So we have to consider the continuous representation by considering integration format that we know. For discrete, we have to consider summation format. For continuous, we have to consider integration format. Instead summation. So here, this expression will be written as x equal 0 to 6 integration lower limit x equal 0 to 6 x rho dx by x equal 0 to 6 rho dx. Okay. We know rho is nothing but psi mod square. So here instead of rho, we just written psi mod square, right? Right. Psi mod square is nothing but psi star psi. So instead of psi mod square, we can write psi star psi. Okay. Here also in the denominator we written same. So here you can see x is a simple operator. X here I can write, and here also I can write. So instead of writing x over here, I can write here. Okay. So the expression will be psi star x psi dx by denominator is same. That implies xcm will be equal to 0 to x equal 0 to 6 psi star x psi dx by 1. Why it is 1? Because if psi is the normalized, then total probability. This is the always total probability. So this value is your 1. If psi is normalized, this value will be 1. So the denominator, this value I written as 1. So this the so-called, here I written xcm, or the probability of finding the particle. Where it is mostly probability finding the particle is represented as xcm. Whatever the expression previously we written, it will be x equal 0 to 6 psi star x psi dx, because denominator we written as 1, which is nothing but total probability. Or we can write expectation value of x. Expectation value of x here, this one, or this one, this expression you can consider. This is your general expression. uh, so xcm, instead of xcm, we have to write expectation value of x, which is nothing but x cap within angle bracket. This is your angle bracket. We have to write x cap will be equal to this much. Here is equal to this much. Whatever written here, same thing I have written over here. Or the denominator is 1, because due to the total probability, this value is always 1. Then we have to write x equal 0 to 6 psi star x cap value. I told initially that this value is your x psi dx. Got it? So here the general expression, if we are going to consider the expectation value of x, or most of the position, or most probable position of the particle in our quantum mechanics or one dimensional dynamics of the quantum particle, is your this one. Expression will be this one. Likewise, any physical observable quantity. So here we consider the position. So position operator, this x cap is your position operator, and the value is x. Similarly, any physical observable quantity, so that suppose a, hence in general, expectation value of any physical observable quantity, suppose that is your a, I will write here, is written as, first I have to write it. Okay, I written over here. Hence, in general, the expectation value of any physical observable quantity, suppose a, is written as a cap is the operator of this physical observable quantity a cap. We has to be written in between the angle bracket. This is the angle bracket, equal to minus infinity to plus infinity psi star a cap psi dx by minus infinity to plus infinity psi star psi dx. So in this video, we have been discussed step by step why and how the expectation value of any physical observable quantity is written in this format. Here, physical observable quantity can be position, can be momentum, can be kinetic energy, can be potential energy, and total energy. Okay. In our next class, we are going to discuss the expectation value of the position of a one-dimensional box, 1D box. like this. If the particle is moving only along x-axis one dimensionally from x equal to 0 to L, what will be its expectation value of the position, that is written as in this format, or the most probable position of the particle, that we are going to discuss in our next class. Thank you so much for watching this video. Thank you.